Hello everyone. In the previous few videos, we have discussed about the aggregate analysis as well as the accounting method of the amortized analysis. In today's video, we are going to discuss about the third technique under amortized analysis by name potential function method. Note that in case of potential function method, we need to define a potential function. We need to initially define a potential function which captures some structural parameters. In the sense, whenever we do some operation on a particular data structure, the structural parameters might be the number of elements present in the data structure. In the sense, what happens to the number of elements whenever we do a particular operation on a particular data structure. Or say, for example, in case of an dynamic hash table, what would be the size of the hash table on performing an insertion operation? In case of a stack, whenever we perform a push operation, we note that every time we perform a push operation, the number of elements in the stack keeps increasing. And reversely, the number of elements keeps decreasing whenever we perform the pop operation. Similarly, the other structural parameter of interest with respect to the binary counter might be the number of ones present after a particular increment operation. That is about the structural parameter. Note that in case of the potential function method, we define a potential function which captures some structural parameters. Note that, let me assume that there is a particular data structure denoted with D. On performing an operation I on that particular data structure D, this I minus 1 gets transformed to I. So this is what it means that whenever we perform some operation on a particular data structure, the state of the data structure gets changed. In the sense, some of the structural parameters on that particular data structure changes. Let it be denoted with this particular function, wherein on a particular operation on performing a particular operation I on a data structure D of I minus 1 gets transformed to D of I. And let me denote phi be the potential function. And on the initial data structure, let D naught be the initial data structure. Whenever I use this potential function phi on the initial data structure, there will be no changes. So it is being initialized to 0. If I use this potential function phi on any operation denoted with I, the data structure, that is the potential function phi of D of I will be having a value of greater than or equal to 0. In the sense, let me denote the amortized cost of performing a particular operation I denoted with Ci dash. The Ci dash is the amortized cost on performing an operation I. This amortized cost is equal to actual cost Ci plus change in potential. Change in potential is nothing but the difference between phi of Di minus phi of Di minus 1. This change in potential is also called as the potential difference. Note that if this potential difference is greater than 0 on performing a particular operation I, if the potential difference is greater than 0, then it implies that the operation I stores some energy. It stores some energy for performing the next operation, the next few operations. Similarly, if delta phi I is less than 0, then it implies that the operation I uses the data which was stored by the previous ith operation. Any of the operation uses the stored data to deliver the operation. Please note this particular equation, that is the amortized cost Ci dash is equal to actual cost plus change in the potential, or we call it as the potential difference. This was with respect to a single operation I. Now the amortized cost on performing n operation can be denoted as that is Ci dash, that is summation of I is equal to 1 to n is equal to summation of I is equal to 1 to n of this entire thing, Ci plus phi di minus phi of di minus 1, which is the potential difference. So this is nothing but Ci dash, that is summation of I is equal to 1 to n is nothing but the summation of 1 to n of Ci plus phi of di. Let me take the nth operation. So this will be phi of dn minus phi of di minus 1. Let me take it as phi of d naught. We have noted that phi of di or any operation will be greater than or equal to 0. In the sense, this part will be greater than or equal to 0, and this phi of d naught will be 0. This was the initialization that we have done. Now with this, I can state that the amortized cost I is equal to 1 to n of Ci dash will always be greater than or equal to summation of I is equal to 1 to n of Ci. Because we have this phi of dn greater than or equal to 0, maybe if it is greater than 0, then summation of, that is the amortized cost of performing n operation will always be more than the actual n operation. So this was about how to define a potential function in generalization. Now we will apply this potential function method for the examples that we have discussed. First we will discuss the example of performing the push, pop and multi-pop operation on a stack. Coming to the example of performing push, pop and multi-pop operation on a stack, let me assume that the structural parameter be the number of elements. In the sense, my potential function, that means this number of elements is nothing but the potential function. Let this potential function capture what happens with respect to number of elements whenever we perform the push, pop and multi-pop operation. First let us consider what would be the amortized cost for performing the push operation. That is the first one, amortized cost of performing the push operation. Let me denote the amortized cost of performing the push operation as the actual cost of performing the push operation plus change in potential. Change in potential was denoted with phi I minus phi I minus 1. I am not using delta of phi I minus 1 minus delta of phi I minus 1. Let me use it as phi I minus phi I minus 1. This was the change in potential. Now what was the change in potential? What was the potential function? Potential function was nothing but the number of element. In the sense, during my I minus 1th operation, let x be the number of element. In the sense, while performing, maybe or after performing I minus 1th operation, in my stack there are x element. Now, what will be the number of element when I perform the ith operation? During I minus 1th operation, it was x. The number of elements were x. Now, if after performing ith operation is the next operation. If I perform a next insertion operation or the next push operation, that is in the ith operation, after performing the ith operation, what happens to the number of elements? The number of elements will be 1 more than x, 1 plus x. Now please apply this here. So this is nothing but what is the actual cost of performing the push operation on the stack? You might have noted the actual cost of performing the push operation on the stack was just 1. It used to take a constant time. 1 plus phi I. What is phi I? It is 1 plus x. It is 1 plus x minus. What is phi I minus 1? After performing I minus 1th operation, I had assumed that x is the number of element. This is x. So what happens? This x and plus x got cancelled. So the amortized cost of performing the push operation is 2. Now in case of the accounting method, if you have noted, for this particular example, for performing push operation, we have taken the amortized cost as $2. For every push operation, we were charging $2. Hope this is clear. this was about the amortized cost for performing the push operation. Let us see what is the amortized cost for performing the pop operation. C dash of pop is equal to C pop plus change in potential phi I minus phi I minus 1. Now here also we'll assume that after performing I minus 1th operation, that is after I minus 1, after performing I minus 1th operation, let x plus 1 be the number of elements. That means after performing I minus 1th pop operation, the number of elements that is left out in stack is x plus 1. Now, after ith operation, what happens to the number of element? After ith operation, the number of elements will be 1 less than the I minus 1th operation. Ith operation, after ith operation, number of elements will be x. Now please apply this here. The amortized cost of performing pop operation is nothing but the cost of performing the pop operation. What is the cost of performing the pop operation? If you have noted, the cost of performing the pop operation was a constant. So this would take 1 plus phi I. What is this phi I? This is the number of elements after performing the ith operation, which is x minus phi I minus 1. Phi I minus 1 is x plus 1. So minus x plus 1. So if you have noted, this becomes 1 plus x minus 1. Minus 1 minus plus 1 got cancelled. Plus x and minus x got cancelled. I'm left out. So its answer is 0. Please compare this with the accounting method. In case of accounting method, in order to perform the pop operation, you might have noted that the pop operation was a free operation. We never used to charge anything for performing the pop operation. Now we'll apply the same thing for the multi-pop operation. Let me denote the multi-pop operation, the amortized cost of multi-pop operation as C dash of multi-pop is equal to C multi-pop plus the potential difference. Now here once again we'll assume that after performing the I minus 1th multi-pop operation, the number of elements let the number of elements be k plus n. I'll assume that the number of elements after performing the I minus 1th operation is k plus 1. In the sense, if you have noted, to perform this multi-pop operation, what was the actual cost? The actual cost was, if I perform a multi-pop for k element, this was actually k. K plus. So phi of I minus 1 is k plus 1. Now what will be ith operation? That means after performing the ith operation, what will be the number of elements? The number of elements will be n. Now apply this here. It is k plus n minus k plus n. So what happens? This is k plus n minus k minus n. N and n got cancelled, k and j got cancelled. So I am left out with 0. So the amortized cost of performing the multi-pop operation is 0. Go back and compare with the accounting method. Even in case of accounting method, we have taken that the amortized cost of performing the multi-pop operation was also 0. So this is how we need to analyze with respect to potential function with the example of stack. Let's go to the second example. Let us consider the example of binary counter and see what happens if I do an amortized analysis with respect to the potential function method. Coming to the example of the binary counter. Now this is an 8-bit binary counter. These are the counter values. I have just taken the counter values from 0 to 13. So this is 0, 1, 2, 3, 4, 5 and so on. Now, in case of a binary counter, let's assume that the structural parameter be the number of ones after performing a particular insertion operation. Hence, I have taken that the structural parameter is the number of ones in the counter. This is my potential function. And note that one thing that you can note is in case of the binary counter, during ith iteration, maybe say for example, if I take the binary counter value 11, now here during ith iteration, all ones after last 0, that means if you consider this 0, 0, 0, 0, 1, 0, 1, 1. After last 0, whatever ones are there, it will be flipped to zeros. It becomes to 0 and this last 0 becomes 1. I'll repeat once again that in case of ith iteration, all ones after last 0, you take any iteration, any insertion operation, after all ones after last 0 will become 1 and that last 0 will become 1 in the next iteration. I have taken here, that means 0, 0, 0, 0, 1, 0, 1, 1. All the ones after last 0 will become to zeros and this last 0 becomes 1. Now similarly, even you can take any other example. Let me take here. Last 0 becomes this. So here, in the counter value 3, 0, 1, 1. After last 0, what are all the ones were there? It changes to 0 and this last 0 becomes 1. Hope this is clear. We'll take this as the potential function. Potential function is nothing but the number of ones in the counter. Yeah, let x denotes the total number of ones before performing the ith operation and let t denotes the number of ones after the last 0. Let me take this same example of the counter value 11. That means at this 11th counter value, the number of x be x. That means the number of ones be denoted with x. Hence, I have taken x value as 3. This is 1, 1, 1, 3 ones. And the number of ones after last 0. This was my last 0. And the number of ones after my last 0 is, let it be denoted with t. And t value is 2. Now, after performing ith operation, there will be x minus t plus 1 once. Now, what will be the amortized cost? So if you write the amortized cost, Ci dash is equal to Ci plus the change in potential, d, write as phi I minus 1. So this is nothing but Ci. What is this Ci? Ci is the actual cost. What is the actual cost? The actual cost is 1 plus t. What is this t? T is nothing but the number of ones. This is the number of ones after the last 0. Hence, the actual cost is 1 plus t plus. Now, what is the change in potential? What is this phi I? Phi I is nothing but after the ith operation, the number of ones will be x minus t plus 1. So, this is x minus t plus 1 minus. Before performing this ith operation, the number of ones were x. So, this is x. So, this will be 1 plus t plus x minus t plus 1 minus x. So, minus x plus x got cancelled, plus t and minus t got cancelled. So, this is nothing but plus 1, 1 and 1. This is 2. If you remember, even in case of the accounting method, we got the amortized cost as 2. That means we used to charge $2 for every increment operation, because in order to flip 0 to 1, we were charging $1, and $1 was stored in the bank, so that when the 1 was later flipped to be 0, I was using that particular one. Even in this case, if you have noted, Ci dash is nothing but $2. Hope this is clear. This was about the potential function method of the amortized analysis with respect to binary counter. Thank you.